Hello. This is lecture. This lecture is about section 2.2 for Math 311, a course in linear algebra at Western Illinois University. And the topic for this lecture will be direct methods for solving linear systems. In the previous lecture, we did some examples about how solving linear systems just by using some basic algebra, some techniques that we've used before, and all of them had to do with working with actual equations. Now we want to sort of standardize this, get a nice algorithm for solving these systems, because sometimes, like in the real world, you'll be working with equations with systems with 10 or 20 equations and 10 or 20 variables. So we want to come up with an algorithm for this. And to start, I just want to do this one example, two different ways. So start with this equation of two equations, two unknowns, and we know that this corresponds to this augmented matrix, where we just take the coefficients and the constant terms, and they become the entries of this matrix. And so the numbers in the first column correspond to the x coefficients, the second column the y coefficients, and the last column is the constants. So we start up, let's solve this system. We can interchange these two equations. That doesn't affect the solution, so we interchange the two rows over here. And then we can change the sign of all the coefficients in the first equation. So we'll basically multiply this equation by -1, so we may multiply the top row by -1. And then we do a thing where we multiply one equation by a constant and add it to another. So we're multiplying this top one again, this time by -3, so the 3x's will cancel out. So when we multiply this by 3, we get -3 plus 6y, and then plus 1. Okay, and if we add it, we're multiplying by 3, so this would be positive 3. So positive 3 plus 2 is 5, and then -3x plus 3x is 0x, and 6y plus 1y would be 7y. Okay, and we don't have to write the x terms here. And then over here we get this matrix. Do the corresponding operation where we multiplied this first row by -3 and added to the second row, and that's how we got this. Now notice we're not really changing the first row in this case, or this first equation. We're just changing the second row. And then in the next one we know we can divide the second equation by 7, or multiply it by 1/7, so we can do the same thing over here. And normally we just go back and plug 5/7 in here, but to do it another way, we can eliminate this -2y by multiplying this equation by 2 and adding it to this. So this would be, we can multiply the 2y minus 2y is 0y, and then the only tricky part here is knowing that 2 times 5/7, right? Plus -1, that's 10, minus 7/7, so that's 3/7. And so we get the solution. And then we get it over here as well. And basically this basically says 1x plus 0y equals 3/7. 0x plus 1y equals 5/7. And that's the solution to this system. You can check this out as it works. But notice that we could basically do all of this over here. We're just doing a series of operations on the rows, and so that we get to solving this system basically means over here getting a matrix which is just 1, 0, 0, 1. Like we'll later say that's an identity matrix, right? Where we can just read off the solutions. So that's what we're just going to do by working this over here and sort of eliminating any variables. Okay, so this leads us to, now notice that on all of these cases, we were either interchanging rows or multiplying one row by a non-zero constant, or multiplying one row and adding it to another row. Okay, so those are precisely what we call the elementary row operations on a matrix. That's what we have here. We have interchanging. First, there are three types. One is interchanging the ith and jth rows. The second is multiplying the ith row by a non-zero constant. And then third one is adding a multiple of a row and adding it to another row. So what this would read is we're multiplying the ith row by alpha and adding it to the jth row, and that's becoming the new jth row. Okay, this means this is now the new ith row, and so on. That's how we denote this. And these are just corresponds to what corresponds to the operations on the equations, which didn't change the solution of the system. So, for example, in our example, this over here, what we did was we interchanged rows 1 and 2. Right here, we multiplied the first row by -1, and then here we multiplied the first row by -3 and added to the second row, and that became the new second row. And then here we multiplied the second row by 1/7, right? And then finally we had 2 times the second row and added to the first row, and that became our first row. Okay. So these are elementary row operations, and they don't really affect the solution, but it makes the matrix simpler. And it's so simple in a case where you can basically read off the solutions. Now, sometimes there will be more than one solution, and we'll talk about how to interpret that. But we have a special form that our goal is. We're trying to put this nice form. It's a special. We have a special name for it. It's called reduced row echelon form, RREF for short. And this is a special case of echelon form, or row echelon form, which your book talks about. And I'm just going to, you can be aware of what row echelon form is, so it's a little more relaxed than what this is. But I'm just going to stick with this, because this will, even though this might have a little harder to, not harder, but a little more calculations to find this form, but you'll get a lot more information from it. Okay. So, what does it mean for a matrix to be in reduced row echelon form? Well, first of all, any all zero rows have to be at the bottom of the matrix. And then the second thing is that the leading non-zero, if you have a non-zero row, the leading non-zero entry has to satisfy three things. It has to be equal to 1. It has to be the only non-zero entry in its column, and it's in a column to the left of any leading entries below it. So basically what's going on here is that here's a 1, here's a 1. The ones have to be in descending order. So the top, the further down you go, these leading ones have to be moving to the right. Okay. So we can see these are all examples of reduced row echelon form, okay, because we can see the leading entry in each matrix in every non-zero row is a 1, right? And these ones are the only non-zero elements in their columns, right? Okay, and of course in this case sometimes if there are any zero rows, they have to be at the bottom. And the nice thing about this is if your augmented matrix is in reduced row echelon form, we're going to see it's very easy to solve the system. And the fact that every matrix can be put into reduced row echelon form by a series of elementary row operations. Okay, there's an algorithm for that. We're going to talk about that in a moment. And then another important fact is the reduced row echelon form of a matrix is unique. That's where these ones come in. These leading ones. When you require the leading entry to be a 1, then you get uniqueness. Okay, and just so you know that the leading ones sometimes they're called pivots. Okay. For example, we had back in our example here, this matrix is in reduced row echelon form. Okay, and we can just read off our solutions that way. Okay, so I want to just give you an example, a couple of examples how we would do this. So given the system, what you do is to start by writing the augmented matrix, and then you use elementary row operations to put it in reduced row echelon form, and then you use that to translate that back into your original variables, and then going from there describe the solution. Okay, so in this case, we're asked to solve this system of equations. There's 3 by 3 equations, 3 unknowns. So what we'll do is we'll start by writing the augmented matrix with this. So 3, 1, negative 1, 1, 2, 0, 4, 2, 6, 5, 2, and 3. Okay, so that's the augmented matrix. All right, now, what you want, ideally you would like the first pivot, or the first leading entry to be up here, and then the next leading one to be here, and the next one to be here. And then sometimes you'll be able to do that, sometimes you won't. But you always want to start out here. You want to start left and go right, and then go by column, and see if you can what the pivot element will be if there is one. Now we would really like here, we would like this 3 to be a 1, and we could do it a couple different ways. We could multiply this first row by 1/3, or that's certainly possible. We could also you can see that we get a 1 by like taking this equation and dividing everything by 2 and then interchanging these two. And I'm just going to do that way just because that'll delay making any fractions, dealing with any fractions. So we're going to multiply the middle row by 1/2. So this is 3, 1, negative 1, 1, 1, 0, 2, 1, 6, 5, 2, 3. So that's 1/2 R2. And then we'll interchange the first and second row. So this was R1 interchanged with R2. Okay, and now we can see we have this as a 1. So the next thing after you get a 1 here is you want to clear out all the other entries in its column and make them 0. And we can do that by multiplying this first row and by -3 and adding it to the second row. And we can also multiply this first row by -6 and add it to the third row. Okay. And if we do that, okay, well, the first row is still unchanged. And then this will be, we multiply -3, okay, so -3 plus 3 is 0. -3 times 0 plus 1 is 1. And -3 times 2 is -6, plus -1 is -7, and then -3 plus 1 is -2. Okay, and then now we're going to use -6. -6 plus 6 is 0. 0 plus 5 is 5. -12 plus 2 is -10. And -6 plus 3 is -3, I think. Okay. All right. So now we're done with the first column. Now we want to go to the second one. And see where our next pivot will be. Well, it looks like we already have a 1 here. Okay. We already have a 0 up here. We just want to make this a 0. So we can make this a 0 by multiplying the middle row by -5 and adding it to the third row. Okay. So The nice thing about it, it gets a little easier because these are just zeros here. So 0 plus 0 is 0. Negative 5 plus 5 is 0. Negative 5 times negative 7 is 35. 35 minus 10 is 25. And then negative 6 plus negative 3 is, let's see, did I do this right? Yeah, we want this to, I'm sorry, we're doing the second row. Negative 2 times negative 5 is positive 10. Positive 10 minus 3 is 7. Okay, so, okay. All right, so now we're done with the second row. And now we go to the third row. Obviously, we want this to be a 1, so we'll multiply the bottom row by 1/25. And we can see that will bring us fractions finally. Oh, and we got a visitor here who was interested in linear algebra as well. Okay, and then now we have our 1 here. We want these two to be 0, so we'll multiply. We want to get rid of this 2, so we'll multiply the bottom row by negative 2 and add it to the top row. And we'll multiply the middle row by, or we want to get rid of this negative 7, so we'll multiply the bottom row by 7 and add it to the second row. And you just have to do a little bit of arithmetic. So again, this will be 1, 0, and then negative 3. We wanted negative 2 plus 2 is 0, and then negative 2 times 1/25 plus 1. Let's see if I did this right. This is, okay, hold on for just 1 minute. Okay, I think this works out okay. This turns out to be 11/25. This is 0, 1, 0. I'll multiply this by 7/25 plus negative 2. This turns out to be 1/25. And this is 0, 0, 1, and 7/25. 7/25. So what did I do wrong here? This is 7/25. That's what I did wrong here. Okay. There we go. All right. You have to do a little bit of fractions, but get a common denominator. You'll be fine. And we get that. This says 1x equals 11/25. Y is 1/25, and z is 7/25. Okay. So this is a case where we get one unique solution. Okay, and in fact, that's always the case when you get like an identity matrix and there's one, in this part, in the first part, in the coefficient part. Okay. Now, let me give you an example where that's not quite, where we don't get a unique solution, and where you can actually determine this from looking at the reduced row echelon form. Okay, so example 2, we will do the same thing here. Write the augmented matrix. 2, 1, 4, negative 1, negative 5. 3, 1, 0, negative 3, 4, 5, negative 1. All right, now I'm not going to, there's really no avoiding fractions in this example, so I'm just going to take this top row and I want to make this to a 1, so I'm going to multiply the top row by 1/2. So this is 1, 1/2, 2, negative 1/2. So this was 1/2 R2. Okay. And once again, we can clear out these other two entries by elementary row operations. So So we want to multiply the top row by 5 and add it to the second row, and multiply the top row by 3 and add it to the third row. Okay, and when we do that and take our time with our fractions, you'll see that this is 0, 11 halves, 11, and negative 5 halves. And then the third row miraculously is also equal to that. Okay, if you do the fractions, for example, you have like 5 halves, 5 halves plus 3. That's 5 halves plus 6 halves. That's 11 halves. Okay, it's just arithmetic. Okay. All right. Now, in this case, whenever you have two rows, I mean, if you have 2 rows that are identical, you can eliminate one of them, right? Just like if if you write a system of equations, there's no point in writing the same equation twice, right? So I'm just going to, what we're really doing is we're multiplying this row and adding it to the bottom row, but we can just replace this. Once we can just replace this with all zeros. Okay, and this really just negative R2 plus R3, becoming R3. Okay, and then we can make this we want it to be our pivot entry, so we're going to want to make this a 1. We have to multiply this by the reciprocal. That's 2/11. So this will be 0, 1. 2/11 times 2/11 times 11. Or rather 2 over 11 times 11, that's 2. And then this will be negative 5/11. Again, just do the, because this is, the 2's will cancel out. And then 0, 0, 0, 0. Okay. And then, we are almost done. We just want to make this 1/2 a 0, so that we're going to multiply the the second row by negative 1/2 and add to the first row. Okay, and when we do that, we get 1, 0, and then negative 1/2 times 2 is negative 1 plus 2, that's 1, and then negative 1/2. Just have to do a little arithmetic. Negative 1/2 times negative 5/11 plus negative 1/2. You got a common denominator. This is going to be 5/22 minus 11/22. So this will be negative 6 over 22, which it reduces to negative 3/11. So that's how we get this. Okay, and this is in reduced row echelon form, but we have to go back and bring the variables in. Okay, what are the equations that correspond to this row? Well, this first row says 1x plus 0y plus z is equal to negative 3/11. Second equation says that 0x plus 1y plus 2z is equal to negative 5/11. And then we can see that, we can take the z terms to the other side, and we're going to see that x and y can be written in terms of z. So x can be written as negative 3/11 minus z. Y can be written as negative 5/11 minus 2z. Okay, and z is just going to be z. Okay, and so what we have here is that we can let z be anything we want, okay, any number we want. As long as x is defined as computed this way and y is computed this way, we'll get a solution, okay? for example, if you let z equal 0, you get negative 3/11 minus 5/11 0. Okay, and that should work. But here we have it. But the important thing is we get infinitely many solutions. And because and z is what we call a free variable. Okay, a free variable means it can be whatever we want it to be. And basically how this works is you get for every non-pivot column, that's going to be correspond to every non-pivot column on the coefficient part of the matrix is going to correspond to a free variable. Okay. So let me just give you one example, maybe that's not on the notes. So before we go on, call this example 3. Let's say we had 2x plus 3y plus z equals 5, and then 4x plus 6y plus 2z equals 9. Now, some of you might be able to recognize that that these coefficients are twice this, but 9 is not twice 5. So we can from this you might see that there is no solution. But if you were to do this by this method, we'd start out with this matrix. Okay, you could do. Then you would eventually, after these you'd have to do a couple of operations, but what you get is 1, 3 halves, 11 halves, 5 halves, and then 0, 0, 0, negative 1. Okay, and actually we could make that positive 1, because once we have something here, we can multiply this bottom row by whatever constant we want. Okay, and but we can see that as soon as we get here, we can stop. Because we're not even though we're not even in reduced row echelon form, because this basically says this bottom row says 0x plus 0y plus 0z equals 1. Okay, and that's not true. And if we could get we could change this a little bit. We could if we actually wanted to put this in reduced row echelon form. So I guess this would be 0 and this would be 1. Okay. It would still be not be a solution. I should say, going back to in our first example, I forgot to point this out, that we have a special name for this algorithm. It's called Gaussian elimination, named after Friedrich Gauss, the very famous German mathematician, probably the most, the top mathematicians in history. They're definitely in the top 3, or he is anyway. So that's Gaussian elimination, and this is and basically in theory you can do this when any system, no matter how big. You just have to start left and go right. Okay. And the way you really want to do this is just practice, and be careful with your arithmetic. Take your time. Okay, unfortunately there's lots of arithmetic and lots of arithmetic errors that can go wrong. Okay, and including me when I was preparing these notes. Okay, so that's Gaussian elimination. A couple other things to throw at you. Have some new terms here. So we have the rank of a matrix. Is the number of non-zero rows in its reduced row echelon form. Okay, so and the reason why now the rank, we're going to redefine this number a little bit differently when we talk about matrices, because there are lots of ways to interpret this thing as a rank, but it's the number of non-zero rows in its reduced row echelon form, and its useful right now is it tells us if there is going to be a unique solution, and in fact how many free variables there are. This is what the rank theorem says, that if A is the coefficient matrix of a system of linear equations, the coefficient matrix is this, where we have, here B1, B2, and so on. Okay, the coefficient matrix is this part. Okay, it's everything in the augmented matrix except the last column. So if A is the coefficient matrix, then the number of free variables in this system is equal to n minus the rank of A, where n is the number of variables, which is also the number of columns in the coefficient matrix. Okay, and as a result, we can see that if this is 0, if there are no free variables, that means that this is 0, and then these n and the rank of A have to be equal. So the system will have a unique solution if and only if the rank of A is equal to n. And we saw that in our examples here. By the way, I should say that if this is consistent, if the solution if the system has a solution. In our last example, that system was inconsistent because there was no solution. Okay, so in fact, I would say going back here, there's no solution here, right? Because 0 is not equal to 1. But in example 1, we could see that there are, in the reduced row echelon form, there were no 0 rows. There were 3 non-zero rows, so the rank was 3. And the n was, there were 3 variables in this case, so there was a unique 3 minus 3 was 0, so there were no free variables. Okay, and there was exactly one unique solution. In our second example, we had exactly 2 non-zero rows. So in this case, the rank was 2, and so we still had 3 n was still equal to 3. 3 minus 2 was 1, and that's so we had 1 free variable, which was z. Okay, so that's the rank. We'll have some more things to talk about the rank later. Another term you should be aware of is a homogeneous system. We say a system of linear equations is homogeneous if the constant term in each equation is 0. And these are particularly nice because, the last term is just, the last column in all your matrices are just 0. Okay, so let me just, I'm going to let you look at these and work these out. So these are both homogeneous. With a homogeneous system, there's always a trivial solution. If you set all the variables equal to 0, then that's always going to be a solution. So it's homogeneous. There's always a trivial solution to a system, a homogeneous system. Whether there are any more solutions depends on the reduced row echelon form of the coefficient matrix. Okay, or doing this process. So if you get in this first case, I'm going to let you, the augmented matrix would be 2, 3, 0, 1, negative 1, 0. Okay. In this case, it would be 2, 3, negative 1, 0, negative 1, 5, 2, 0. Okay. And I will let you work on these on your own for now, but let me tell you that I worked the last example out ahead of time, and you can just pause the video and write this down somewhere after you've tried this yourself, and you'll see that here we have, once again, we have a, you'll see that we have the reduced row echelon form here our rank is 2 in this case. Our number of variables is 3, so we get one. Once again, we have one free variable z, which is right here. Okay, and we'll see that this is actually, the solutions can be described with either z, or you can replace z with any letter you want, or t. This will be a line. So, and in fact, remember, these are planes that have two planes, and in this case they intersect in a line. Okay, so remember, a homogeneous system of m linear equations and n variables, it always has a trivial solution, but if m is less than n, it will have infinitely many solutions, and that's because that this, if n at this, the rank is bounded, right, by the number of rows, right? The biggest number, it can't be any bigger than the number of rows, and if the number of rows is m, then the number of rows equals the number of equations, and so if m is always less than n, then this number here is always going to be positive. So we'll always get some free variables, and we'll always have infinitely many solutions. Okay. Again, do the problems in the textbook. Take your time. The best way, that you're not going to learn this unless you practice. So start working on the problems, and I will see you next time.